Okay, so here we begin lesson number 5, and this is all about magnetic fields. So in the first bit of this unit, we looked at circuits and current electricity, and now we're going to shift and talk about magnets, but specifically electromagnetism. So basically, we're going to introduce the basic magnetic theory that you're going to need to know, and really magnetic forces are very similar to some of the other types of forces that we've talked about. We've talked about gravitational forces, right? So the force of gravity that keeps the moon in orbit around the sun, the Earth in orbit around the sun, or the moon in orbit around Earth. We've also talked a little bit about this kind of fact that there's an electric force because that's why positive and negative charges attract and why like charges repel. So this is another type of force. But the magnetic force we see between a north pole and a south pole of a magnet. And we don't fully understand magnetic character yet. It's one of the regions of science that we're still working to develop a full, complete understanding. We're pretty much there, but there's a few lingering things that we don't fully understand. But magnetic character is attributed to what we call domains. Okay, and so there's this theory, it's called domain theory, and it basically says that all large magnets are made up of many magnetic regions called domains. Okay, so the magnetic character of a domain comes from the presence of even smaller, little tiny magnets called dipoles. And dipoles interact with neighboring dipoles, and if they all happen to line up in one direction, you get this magnetic domain. And then if many magnetic domains line up, you get a magnet. Okay, it's one of the reasons why, you know, we can make something smaller and smaller. Like if you chop a magnet in half, you don't get a north pole and a south pole. You get two mini magnets. You get a north pole and a south pole over here, and you get a north pole and a south pole over here. And the more and more and more you chop those magnets up, you just keep on getting more and more smaller magnets until you're down to the size of a domain. But basically, the law of magnetic forces states that similar magnetic poles repel one another, and dissimilar magnetic poles attract one another. Okay, so we knew that from before. That's kind of a recap of some pretty common science that you are probably very well aware of. And something else that you've probably done is looked at magnetic field lines, because they're very easy to recreate if you have a bar magnet or a horseshoe magnet and some iron filings. But basically, the way that magnetic field lines look is if you have a north and a south over here. Magnetic field lines, of course, curl around, and we have a convention that we always use. We always say that magnetic field lines always point towards the South Pole. So they go from the north to the south. And so basically, this is what happens all the way around the magnet. And the way that we get these is that if we pretended that there was a compass here, which way would the compass point? Well, the north end of the compass would point to the south, and the north end of the compass would point to the south, and the north end of the compass would point here. So this is the way that the compass would point. And it would indicate to you the direction of the magnetic field. Okay, very similar here, and of course we get these magnet field lengths coming out like this, and they would all be directed towards the south. Okay, so of course you've seen some of these iron filings. These are some really beautiful diagrams, but of course these don't have the arrows. These don't indicate the direction of the field. But we can, of course, draw in a north and a south, and we could envision, but this is basically what these field lines look like. Here, these two poles, if you were to guess, these two poles would, of course, be similar, right? So they would either be two north or they'd be two south, because the field lines, of course, go in a way that was different. If these were two opposite poles, the fields would go straight across. So let's talk, you know, that's kind of the basics of magnetism, and it's out of the way. Now let's talk about the interesting stuff, which is electromagnetism. And for many years, scientists really worked on the link between electricity and magnetism, and they are very related. But this guy named Hans Christian Ørsted was giving a lecture at the University of Copenhagen, and he discovered a link between electricity and magnetism kind of by accident. He had this big, great electrical demonstration that was apparently set up on the stage, And every single time he'd turn it on and current would start to flow, he noticed his magnet kind of go whoop, and he'd turn it off and the magnet would, of course, go back to normal, and he'd turn it on again and the magnet would move again. And so he couldn't figure out, why is the current that's going through my demonstration affecting my compass? And it's because whenever you send current through a conductor, you create a magnetic field. And that was what Ørsted's principle said. The magnetic field around a straight conductor, basically what this tells us is that charge that moves through a straight conductor, so any current that flows through a wire, produces a circular magnetic field around the conductor. So just like this little diagram here, this is a circular magnetic field all the way around. And really, this discovery led us to realize that charge moving through a conductor generates a magnetic field, and so Ørsted went on to develop a series of hand signals, and these are known as the right-hand rules. And this helps you to understand which direction the magnetic field points, because we want to know it. We want to know which direction the magnetic field points. So, right-hand rule number 1 is for a straight conductor. Okay, so just like the diagram above, you put your thumb in the direction of conventional current. We should make sure that we say that this is conventional current flow, not electron current flow, but conventional current flow. Your fingers then indicate the direction of the magnetic field. Now, it's a little bit difficult to demonstrate this to you without a diagram. However, if you look, and very conveniently so, in your textbook, there's a great diagram of the right-hand rule for a straight conductor, and you should definitely go and look at it now, just so that you see it. We will practice these in class. This is something that will take a lot of time practicing. However, there's other configurations of wire. What happens if we curl the wire up like this? This is called a solenoid. And so if we coil this wire like this, you can see that the iron filings are producing a magnetic field that looks very much like a bar magnet. So here's a little example. Here, let's say we take a conductor and we coil it in a circle. Well, the magnetic field up here, if I put my thumb in the direction of the current, using right-hand rule number 1, my thumb's in the direction of the current, I get a magnetic field that looks like this. Right? Here, if I put my thumb in the direction of the current, I get a magnetic field that looks like this. It's kind of hard to see these little arrows, but they are there. Down here, if I put my thumb in the direction of the field, I get a current that looks like this. The dotted line means it goes in behind. And over here, I get a magnetic field that looks like this. So here, like in this region right here, I've got a magnetic field going in, a magnetic field going in, a magnetic field going in, and a magnetic field going in. So we could summarize this by using right-hand rule number 2, which is that if you put your fingers in the direction of the current for any coil or any solenoid, your thumb indicates the direction of the magnetic field. And in this case, that would be into the page. So we kind of have to think in 3 dimensions for some of these, because we're talking about things coming out of the page and things going into the page. And so that's what makes these a little bit tricky. Okay, so here's right-hand rule number 2, is that you put your fingers in the direction of the current that goes through the coil, and your thumb will indicate the direction of the magnetic field. And we've discovered basically a way to create an electrically powered bar magnet, which is an electromagnet. Thousands of applications of electromagnets, and these are some of the most interesting applications of electricity and magnetism. Okay, so here's a couple examples. For each of the following images, sketch the magnetic field around the conductor. So here is a bar or a current, and it's got some current flowing down it. And so basically what we see here is if I have current that's flowing in this direction, so to the right, got current that's flowing to the right in this direction, and I use my right-hand rule, that means that the current comes out in front and then back up in the back. The magnetic field comes out in front and then up through the back. Comes out in front and then up through the back. What about something that looks like this? So here we'd use right-hand rule number 2, and we'd say, okay, I've got my fingers that are wrapping in the direction of the coil up. And so the direction of the magnetic field is either this way or it's this way. And of course, if you do it, it goes in this direction if you use the right hand rule. All right, so let's talk about the strength of an electromagnet, because there's a couple factors that really affect this, and this will determine what we're going to talk about tomorrow, which is the motor principle. And so here, basically, let's summarize a few of these things, and then we'll talk about an equation or a relationship that might describe it. So the current that flows in a coil definitely affects the strength of the electromagnet. As the current increases, the magnetic field increases. Okay, so that's a big one. Okay, and so this is a linear relationship. B2 over B1 equals I2 over I1. B is the symbol we use for the magnetic field. Okay, the number of turns in the coil, as the number of turns or the number of coils increases, the magnetic field increases. Okay, so B2 over B1 equals N2 over N1, where N is the number of curls or the turns or coils, whatever you want to call it. If we put, say, into the middle of all these coils, let's say we put a material, let's say we put a magnetic material. If the core is ferromagnetic, the magnetic field increases. Okay, so B2 over B1 equals mu2 over mu1. We're not going to use this equation very much at all. This just represents the magnetic permeability of the substance in the middle. We probably won't encounter this too much in this course, but it's just there so that you know that if you put something that's magnetic into the middle of one of these coils, it gets really, really magnetic. You can really increase the strength. And then also the size of the coil. As the diameter gets smaller, the magnetic field gets bigger. Okay, and we're not going to summarize this using an equation, so don't worry about it. But as the diameter decreases, the magnetic field increases, and so that's something you can know. Okay, so that's the strength of an electromagnet. Let's do a quick example, and then we'll call it a lesson. What happens to the strength of the magnetic field around a coil if the current through the conductor is increased from 1 amp to 2.5 amps? All right, well, here's A. I've got I1 and I2. So I've got my initial current, which is 1, and my new current, which I'm going to increase it to, is 2.5. Well, I want to know what happens to the magnetic field. So I've got B2 over B1 equals I2 over I1. And I can simply replace this with 2.5 over 1. So the new magnetic field is exactly 2.5 times what the old magnetic field was. Okay. Part B says what would happen to the field strength if the number of turns in the coil were reduced by half and the current stayed the same. Well, here I've got N2, the new number of turns, is equal to a half what the original was. So B2 over B1 equals N2 over N1. And I can simply replace N2 with my new value. Cross this out. B2 equals 1/2 B1. So the magnetic field would go down by a half. If you cut the number of coils in half, the magnetic field goes down by a half. And that's all she wrote.